Chapter 3 covers PC model, the phase change model. Here, I'm going to go over the essential part of PC model and what is needed to quickly obtain properties such as enthalpy or entropy for phase change fluids such as water, H2O, R134A, etc. So suppose, let's start with very fundamentals here. Suppose we have some liquid in the piston cylinder assembly where we can control the pressure inside by putting a suitable weight. So let's assume it's water. So if you want to draw the state of water on a TS diagram, let's pick an arbitrary point, let's say state 1 right now. And let's do a thought experiment. Suppose we add a little bit of heat to the water using, say, an electrical circuit, and just a little bit of energy is added, and then we let the water come to equilibrium again. So piston is insulated, so there is no heat transfer, etc. It comes to a new equilibrium. We understand if we add energy, temperature will increase of a liquid, so we'll go somewhere here. Entropy will also increase because when heat is transferred, or in this case, if electrical wire generates entropy, the entropy of the water will increase. As temperature rises, we know entropy increases. If we keep going like this, then a point will be ultimately reached, at which point we call it the F point, or the saturation point for water. What happens is that after that, any further heating generates bubble inside the water. So if we add any more energy, the temperature will not change anymore. We call that the boiling temperature or the saturation temperature of the fluid, T sat, at which point the state will keep going towards right, entropy will keep increasing, but temperature will not. And finally, as we keep adding energy, of course the fluid will expand and all the liquid will be converted to what is known as saturated vapor state, or the G state. At that point, what we got is pure vapor, and if we add any more energy without changing the pressure in the same constant pressure line, the temperature will start rising again. So this knee-shaped curve, a constant pressure line, is characteristic of a phase change model. If we repeated the experiment at a higher pressure, the line would have shifted up and looked something like this. All these F points, when joined, we call it an F line, and all these G points, when joined, called the G line, produces this characteristic dome shape. On the right hand side, we have pure vapor, superheated vapor. On the left hand side, we have subcooled liquid, and inside the dome, we have a mixture of saturated liquid and saturated vapor. So once again, the essence of a PC model is that the dome separates the three different phases of the fluid. Here it's liquid. At F point, even at F point, a fluid is pure liquid. It's called the saturated liquid. At G point is pure vapor. And in between, we have liquid and vapor mixture. So let's go and see how we find properties of a PC fluid given two independent properties, two independent thermodynamic properties. Well, the standard thermodynamic properties are what? They are P, T, V, U, H, and S. For any kind of working substance, this set of properties constitute what is known as a thermodynamic state, only two of which are independent. If you know any two, you can find the third. In case of a PC model, especially if you're inside the dome, a new property called the quality is very important to know, because when you have a mixture, which is a mixture of F and G states, the quality X is the mass of vapor divided by the total mass, vapor and liquid. We know the vapor is the G state, so you can also write it as mass of the G state, F plus G. So the quality kind of quantifies how much vapor is present in a mixture of vapor and liquid. So if X equals 1, it's a pure vapor. If X equals 0, it's pure liquid. And somewhere between, suppose X equals 0.5, then we have a mixture of liquid and vapor in 50-50 proportions. Of course, if H2O or the fluid happens to be superheated vapor, X has no meaning. Subcool liquid, likewise, X has no meaning. So X only has meaning from F to G states. For F state, X equals 0, and for G state, X equals 1. Okay, suppose now we are to find the state of a particular, say state 1. The temperature is given and it's said that it's a saturated liquid. Find enthalpy. So we have 200 degrees Celsius water. Again, all these problems we'll be solving involving H2O, but the same concept can be used for any other fluid. So we notice that saturated liquid means X equals 0. So two properties are supplied. So we go to property tables, PC model, and select the saturation table, pressure saturation table in this case, or temperature saturation. So there are two saturation tables, as you can see. In the temperature saturation, the only difference is that the temperature appears as the first column in the temperature saturation table, whereas the pressure appears as the first column in the pressure table. So because in this problem the temperature is given to us 200 degrees Celsius, we can go and pick up the properties of F and G states. Notice how they are arranged: Vf, Vg, Uf, Ug, Hf, Hg, etc. And the corresponding pressure is listed on the second column. So to find enthalpy of the saturated liquid, it must be Hf column at 200 degrees Celsius. So we go and pick it up here. Hf is 852. We'll just not write the unit every time because these are standard SI units. We'll go back and verify this now using a test calc to make sure we got the right answer. And test calc can be launched right here. If it is just about finding properties, they're all bundled together. So you click on the PC test calc cell here and the test calc will appear right below. So in this problem, we know the temperature and saturated liquid mean the quality is supplied, which is X is 0. And notice it produces the phase of the liquid is shown here, saturated liquid, and enthalpy is found, verified. And if you do a TS diagram, that should show that state 1 should be on the F line, showing it's a saturated liquid. So that's a visual check on the calculated state. Okay, let us go and find more states. Suppose we are to find another state, let's say state 2, same temperature, but the quality is supplied. Suppose quality is 0.9. And find entropy. Suppose the question is find S. Well, What does quality mean? Quality means that we have, in this case, 90% of the mixture has vapor in it and 10% is liquid. So first find SF at 200 degrees Celsius and Sg at 200 degrees Celsius. And so S will be a weighted average of the two. 1 minus X, which is the liquid fraction, times property of liquid, plus X, which is the vapor fraction, times Sg. So this is a standard formula used for any mixture where if you know the quality and the saturated SF, the property at F and G points, then it's very easy to find entropy or enthalpy or any other property for that matter for the mixture. So suppose the question is find S in this case. So we'll find this two values, substitute them here, 1 minus 0.9, and we'll pick up SF and we'll pick up Sg, and that'll be our answer. So what is SF? We go back to, okay, let's start a new tab where we'll have again the temperature saturation table at 200 degrees Celsius. We are to pick up SF and Sg, which is 2.33 and 6.43. Which turns out to be about 4.38. Let's go and verify this again using test calc. We go back to our test calc page, which is temperature is already 200 and quality is not 0, it's 0.9, and we get an entropy of 6.022. Oops, so we must have made a mistake. Let's go back here. Oh yes, we did make a mistake. 6.022. And it makes sense. Think about it. 90% of the mixture is superheated vapor. Superheated vapor has 6.643 entropy and liquid is 2.33. So it's more weight towards the vapor. So this is the correct answer. Okay, suppose now we have a little more complicated problem. Let's say we are trying to find state 3 and pressure is supplied, and instead of quality, what is supplied is suppose enthalpy. Let's say enthalpy is given as 2576 and we are supposed to find entropy. Okay, so let's see how we go about it. The first thing to do is to again draw the TS diagram, draw the dome, and we have no clue where the state lies. So we draw a 1000 kPa line, and this is my F and G state. So the first thing to do is to find, we know enthalpy, let's find SF at 1000 kPa and Sg at 1000 kPa. Our goal would be then to compare our known H with these two values. We know the state will lie somewhere on this 1000 kPa line to figure out whether we have a superheated vapor, subcooled liquid, or a mixture. So let's go to the table. This time for 1000 kPa, we will go to the pressure saturation table because that's the first column. So go to 1000 kPa, which means 1 MPa. And at 1 MPa, this is the line, and the enthalpies are here, 762 and 2778. So let's pick up these values, 762 and 2778. Notice this is bracketed by these two values, so obviously we have 2576, somewhere here would be our state. So this is our state 3. To pin it down, we can calculate the x value, because we know h would be what? 1 minus x times hf. Sorry, these are not entropies, these are enthalpies. So this is our standard mixture formula, and if we substitute h, hf and hg, you can solve for x and show that x equals 0.9. So our question is to find enthalpy. So we can now find enthalpy by simply using the same formula, except this time it would be for entropy. To find entropy S, we find the value of SF and SG here. 1 minus 0.9. SF is, if you go back to the chart, I already picked up the value. This is SF, and SG is 6.586. Solving, we get an entropy value of 6.142. Just to verify, first let's go back to the table to make sure I picked up the right SF and SG. At 1000 kPa, which is 1 MPa, 2.18 and 6.58. So these are the values I picked. So finally, let's go to test calc and make sure we can calculate state 3. 1000 kPa is known, and enthalpy was given 2576. So we just enter it here, and here comes quality, which is 0.9, and entropy is 6.14. So therefore we have just verified our result, and we found the entropy in this mixture state. Okay, now suppose we are after another state, state 4, and what is given is pressure is again 1000 kPa, and let's say temperature is supplied 520 degrees Celsius. Once again, we draw the state. We try to pin it down on the TS diagram, and this is our 1000 kPa line. We know the state will be somewhere along this line, but we have no clue whether it's liquid water, a mixture, or superheated vapor. So first thing to do in this kind of situation is to figure out what is the saturation temperature, Tsat at 1000 kPa. If you know the saturation temperature, then we can compare our given temperature 520, and we'll know whether we are on the superheated part or the subcooled part of the dome. So we go to the saturation table. We open the pressure saturation table, which is already open. Go to 1000 kPa, which is 1 MPa, and look at the boiling temperature, which is 180 degrees Celsius. The saturation temperature is 180 degrees Celsius. So this is the temperature, which is 180. So 520 is obviously somewhere up here. So this will be our state 4. We have found the intersection. It's superheated vapor, obviously. Anything above 180 degrees Celsius will be superheated vapor. So let's say we are supposed to find enthalpy and entropy. So how do you do that? So to find enthalpy or any property of a superheated vapor, it's rather simple. You go to the superheated table and look for the pressure. So they are tabulated according to pressures. If you know the pressure you lugged out, this is the table, and 520 degrees Celsius, hopefully it belongs here. Oops, it's between 500 and 600. For accurate values, one can interpolate, but there is really no point because we have test calc to verify our solution. The best idea is to kind of eyeball your answer. So enthalpy is 3478 and 3697. So 520 is closer to 500. So maybe we'll pick up 3500 as our value. Entropy, similarly 7.76 and 8.02, maybe we'll pick up 7.78, let's say 7.8 or something as our value. So using these approximate values, we can write enthalpy is 3500 and entropy is, let's say, 7.82. If we go to test calc to find the exact values, which are here, so we go to state 4, pressure is 1000 kPa and temperature is 520 degrees Celsius, and let's see, 3522 and 7.82 are the exact values. So even if I eyeball it to be 7.8 or 3500, these answers are pretty close. So this is how you find properties of superheated vapor. The only time it becomes a slightly challenging problem, what if the pressure was not 1000 kPa? What if the pressure was somewhere in between? Suppose we have the table for 1000 kPa and 1200 kPa. Suppose the pressure supplied was 1100 kPa, which is in between the two tables. Then what you do again, the interpolation is between two different tables, so you have to use your judgment. You have to bracket your, suppose the temperature given is 400 degrees Celsius, then say enthalpy for 1000 kPa and enthalpy for 1200 kPa, so you can eyeball again and find an interpolated value. So in other words, interpolation is a skill. If you do by hand correctly, it will take a long time to get a number, whereas if you learn how to estimate by just interpolating, by bracketing your answer, you can get a very close answer quite fast. If you verify your answer with test calc, you will develop the skill very quickly, and you will see that when you mentally interpolate, eyeball the answer, you will get a better idea about the numbers than if you just put them in a calculator. Finally, let's see how we find properties of a subcooled liquid. Let's say state 5, what is given here is the same pressure, but the temperature is only, let's say, 20 degrees Celsius. Well, because for 1000 kPa we already figured out the saturation temperature. We know this is going to be a liquid, temperature is way below 100, so this will be our state 5. So we identified the location of the state in the subcooled region. Question is, how do we find properties of a liquid? Even though for water there is a compressed liquid table, generally compressed liquid tables are not available for most fluids. So we have to find another way to find liquid properties. And the liquid again, if you go back to our handout on all these models, let me open another tab and go to table J, which is our formula sheets, and you go back to different models and find the PC model, which tells you what we have been doing so far. And for the liquid, there is this subcooled liquid model that is used. It's called also compressed liquid submodel. And essentially the idea is that the main idea of the liquid model is that VUS depend on temperature only. Let's understand that. Going back here, it says that let's do it on a new page. So you want to find the properties of a subcooled liquid, which is very valuable for handling problems such involving a pump, for instance. So let's say we have a state here for which we want to find, this is our state 5, we want to find properties. So the model says that V at state 5, V, U, and S, they all are function of temperature alone. So in other words, if we find properties, if the state belongs anywhere on this horizontal line, on this temperature, constant temperature line, then VUS will be the same value. So therefore, if we can find the properties of this F state, then you can see immediately that V at 5, suppose we want to find specific volume at state 5, it will be same as VF at the temperature 5. So if you know the temperature at state 5, that's all. Then V, U, and S also can be found the same way. U at 5 will be UF at the given temperature, and S at 5 given temperature. It's as simple as that. So if you know the temperature, all you have to do is to find the F state, and that will give you V, U, and S. But how do you find enthalpy? Enthalpy, unfortunately, is U plus PV, will always depend on pressure. U, you already know how to find. So if you know the pressure, this is the formula we're going to use to find enthalpy. So in this particular problem, where the temperature is supplied 20 degrees Celsius, so therefore we can go and at 20 degrees Celsius, if we go to the temperature saturation table, we can pick up at 20 degrees Celsius what is our VF, which is 0.001, what is our UF, 83.95. So if you have to find U, .001, that's what you saw. Oh, the pressure is 1000 kPa, not 1000 Celsius. So what will be enthalpy? U plus PV plus 1000. So it's just 84.45. So this is how we find enthalpy of a liquid. If you want to verify, verification is always the same way. We can go to our test calc, state 5, 1000 kPa, and temperature was 20 degrees Celsius. Notice the phase has been found as part of the solution, subcooled liquid, and enthalpy is found about 85, pretty close to what we got, and all other properties are displayed here. Just one more note about the enthalpy of liquid. In many problems, entropy doesn't change. Isentropic devices such as a pump handles liquid. Now suppose we have a saturated liquid at state F, and we are raising its pressure using a pump where entropy doesn't change. So if entropy remains constant, and we know for liquid entropy is a function of is same as finding F state at T. So therefore, if entropy remains constant, then entropy is a function of temperature alone. So if entropy is constant, T must be constant for a liquid. If temperature remains constant, you can see that enthalpy becomes so if temperature doesn't change, this part and that part doesn't change. So therefore, change in enthalpy, suppose between two state H2 minus H1, of a liquid, then in that case, these terms will get cancelled out, and you can see it will become P2 minus P1 Vf at T. So if you want to find enthalpy of a liquid, this becomes a very handy formula. In other words, if you know liquid enthalpy at a given point, then you can find the difference from just the pressure difference multiplied by the specific volume at the temperature, which is remaining constant. Again, it's only true for an isentropic situation. As we solve more problems, say involving a vapor power plant, these steps will become clearer.